Welcome! In this session, we'll tackle an interesting problem, number 1612, check if two expression trees are equivalent. We'll break down the problem, explore various approaches, and provide a clear solution to help you understand this concept. Let's get started. In this problem, we are tasked with determining whether two binary trees, each representing an expression, are equivalent. These trees are structured such that the leaf nodes, which have no children, represent variables. Each variable is a lowercase English letter, like a B or Z. On the other hand, the non-leaf nodes, which are internal nodes, represent the plus operator. Now, for two expression trees to be considered equivalent, they must evaluate to the same value regardless of the order in which the operations are performed. Essentially, this means the trees are equivalent if they represent the same multiset of variables, regardless of structure. Our goal is to implement the function check equivalence, which takes the root nodes of these two trees as input and returns a Boolean value true if the trees are equivalent and false otherwise. Let's look at an example to understand this better. In example 1, we have two trees. Tree 1 has the root node plus with children at and b, while tree 2 is also rooted at plus but with children b and a. Both trees represent the expression a plus b. Since the order in which you add the variables doesn't matter, the two trees are considered equivalent. The function should return true in this case, as the trees evaluate to the same multiset of variables. Now, consider a slightly more complex case in example 2. Here, tree 1 has the root node plus with children at and another plus node, which itself has children b and c. This represents the expression a plus b plus c. Tree 2, on the other hand, has the root node plus with children and c, and the c node has a child node b. This represents the expression a plus c plus b. While the structures of these trees differ, both contain the exact same variables of b and c with the same frequencies. Therefore, these trees are equivalent, and the function should return true. In example 3, the two trees are no longer equivalent. Tree 1 has the root plus with children at and b, representing the expression a plus b. Tree 2 also has the root plus but with two nodes as its children, representing the expression a plus a. Here, the variables and their frequencies do not match between the two trees. Specifically, tree 1 has 1 and 1b, while tree 2 has 2 a's and no b. Since the expressions are not equivalent, the function should return false in this case. Finally, there are additional constraints and edge cases to consider. For instance, with single-node trees, where each tree contains only one variable, the function should return true if the variables match and false otherwise. For unbalanced trees, even if the structures are different, the expressions might still be equivalent if the multisets of variables are the same. Another edge case involves trees with duplicate variables, where the same variable appears multiple times. The solution must also handle large trees with up to 100 nodes efficiently. These considerations ensure the function works correctly across all possible inputs. To determine if two expression trees are equivalent, one possible approach is to use a brute force method. The intuition here is to traverse both trees and generate a string representation of their expressions. Once we have these strings, we can sort the characters in each and then compare the two sorted strings. If they match, it means the trees are equivalent. The steps involve a traversal, such as in order or pre-order, to collect all the variable names from each tree, concatenating these variables into a string, and finally sorting and comparing the strings. The time complexity for this approach is n log n, where n is the number of nodes, due to the sorting step. It also requires n space to store the string representation of the trees. However, this method comes with drawbacks. Sorting introduces unnecessary overhead, and this can become inefficient for very large trees. While it's simple to implement, the additional cost of sorting makes this approach suboptimal. A more efficient way to solve this problem is by using an optimized approach based on a frequency count of variables. Instead of generating and sorting strings, we use a frequency map, such as a dictionary, to count the occurrences of each variable in both trees. The key insight here is that the order of variables in the trees doesn't matter, only their counts do. By comparing the frequency maps for both trees, we can determine if they are equivalent. The steps involve traversing the first tree and recording the frequency of each variable in a dictionary, repeating the same process for the second tree, and then comparing the two frequency maps. This approach has a time complexity of O(n), where n is the total number of nodes across both trees, and it requires only O(1) additional space since the frequency map is limited to a fixed number of variables, a to z. This method is more efficient than sorting and scales better for larger trees, making it a clear improvement over the brute force approach. The chosen strategy for this problem is the frequency count of variables approach. This method was selected because it offers both time and space efficiency. The brute force approach, which relies on string generation and sorting, was rejected due to its higher time complexity, O(n log n), and the unnecessary overhead introduced by sorting. By using a frequency map, we avoid the need for sorting and achieve a simpler, faster solution. Comparing the two approaches, the brute force method is easy to implement but becomes inefficient for large trees due to the sorting step. In contrast, the frequency count method has an optimal time complexity of O(n), and scales well for larger inputs, though it is slightly more complex to implement. The key insight driving this choice was recognizing that the order of variables in the trees is irrelevant, only their counts matter. This realization allowed us to shift from sorting strings to using frequency maps, leading to a significant improvement in efficiency. The problem we're tackling involves determining whether two expression trees are equivalent. An expression tree is a binary tree where the leaves represent operands, such as variables or constants, and the internal nodes represent operators like addition, subtraction, multiplication, or division. The goal is to check if these trees compute the same result for any set of input values, even if the structures of the trees are different. Our approach begins with a brute force method. First, we validate the inputs to ensure both are valid binary trees. If either tree is null, we handle this edge case by returning true only if both are null, otherwise, we return false. Next, we traverse each tree to generate string representations of the expressions they encode. This is done using an in-order traversal, which respects the structure of the tree while incorporating parentheses to preserve operator precedence. For instance, if the tree represents the expression a plus b asterisk c, the traversal would generate the string a plus b asterisk c. Similarly, for the expression a asterisk b plus c, the string a asterisk b plus c is generated. Once these strings are obtained, we normalize them to account for commutative operators like addition and multiplication. This involves rearranging operands consistently, such as converting a plus b and b plus n into the same standardized form. By doing so, we ensure equivalent expressions will have identical normalized strings. After normalization, we compare the strings generated from both trees. If the strings are identical, the trees are equivalent, and we return true, otherwise, we return false. Additionally, we handle several edge cases. For example, if both trees are null, we return true. If only one tree is null, we return false. Trees with different structures but equivalent expressions, such as those involving commutative operations, should still return true after normalization. However, for operators like subtraction or division, which are non-commutative, we must ensure that the order of operands is preserved during normalization to avoid incorrect results. By carefully managing these nuances, we can accurately assess equivalence. Now, let's analyze the complexity of this approach. The traversal of the two trees requires time proportional to the size of the trees, which is n1 plus n2, where n1 and n2 represent the number of nodes in the respective trees. Comparing the normalized strings, which have a combined length of m, takes m time. Therefore, the overall time complexity is n1 plus n2 plus m. In terms of data structures, we use binary trees to represent the expression trees, where each node stores a value and pointers to its children. Strings are utilized for storing the generated expressions, and stacks are employed during traversal to handle parentheses and operator precedence. Let's walk through an example. Imagine tree 1 represents the expression a plus b asterisk c, and tree 2 represents asterisk b plus c. First, we perform in-order traversal to generate the strings. For tree 1, the string is a plus b asterisk c, and for tree 2, it's asterisk b plus c. Then, we normalize these strings. For commutative operators like addition, we sort the operands, resulting in both trees being normalized to a plus b asterisk c. Finally, we compare the strings. Since the normalized strings are identical, We conclude that the two trees are equivalent and return true. Now, let's consider an edge case. Suppose tree 1 represents the expression ab plus c, while tree 2 represents c plus ab. After generating the in-order traversal strings, tree 1 produces ab plus c, and tree 2 produces c plus ab. During normalization, we account for the commutative property of addition, ensuring both strings are rearranged consistently. This process results in the normalized string ab plus c for both trees. Comparing these strings confirms they are identical, so we determine that the trees are equivalent and return true. This Python implementation solves LeetCode problem number 1612. Check if two expression trees are equivalent. The goal is to determine if two binary expression trees represent the same expression by comparing their variable counts. First, we define a node class to represent the binary tree nodes. Each node has a value, val, and optional left and right children, left, right. The check equivalence method is the main function. It takes two tree roots, root 1 and root 2, as inputs. The core idea is to count the occurrences of each variable, leaf nodes, in both trees and compare these counts. The helper function collect_count traverses a tree and collects the variable counts into a dictionary. It uses a stack for iterative traversal to avoid recursion depth issues. For each node, if it's a leaf, both children are none, the count for its value is increment in the dictionary. If the node has children, they are added to the stack for further processing. Once the variable counts are collected for both trees, count 1 for root 1 and count 2 for root 2, we simply check if the two dictionaries are identical. If they are, the trees are equivalent, otherwise, they are not. This approach ensures efficiency, as each node is visited once, making the time complexity O, n plus m, where n and m are the number of nodes in the two trees. The space complexity is also O, n plus m, due to the dictionaries and stack usage for traversal. The code is concise and handles edge cases, such as trees with different variable distributions, gracefully. It is production ready and adheres to best practices for clarity and efficiency. Here, we start by defining the structure for our binary tree nodes using the node class. Each node holds a character value, as well as references to its left and right children, which are initialized to null. Then, we move on to the solution class, where the main logic resides. The check equivalence method takes two root nodes of expression trees as input and determines if the two trees are equivalent. To do this, it uses a helper method called collectCount to traverse each tree and create a frequency map of the characters found in the leaf nodes. By comparing these two maps using the equals method, we can check if the trees are equivalent. Next, we begin implementing the collectCount method by initializing a hash map to store the character frequencies and a stack to facilitate iterative tree traversal. The root node is pushed onto the stack to kick off the traversal process. Then, we enter a while loop that will continue as long as there are nodes in the stack. Inside the loop, we pop a node from the stack to process it. If the current node is a leaf node, meaning both its left and right children are null, we update its value in the count map. This is done using the getOrDefault method, which retrieves the current count for the character or defaults to 0 if it hasn't been seen before, and then increments it. For non-leaf nodes, we check if they have right or left children, and if they do, we push those onto the stack to process later. This ensures that all nodes in the tree are visited iteratively. Once the stack is empty, meaning all nodes have been processed, we return the count map containing the frequency of each character found in the leaf nodes. This map is then used in the check equivalence method to compare the two trees. This implementation ensures an efficient and clear approach to solving the problem. This problem is about determining whether two binary expression trees are equivalent. In these expression trees, the leaf nodes represent variable names like A or B, while the internal nodes represent operations, such as the plus operator plus. The key idea is that two trees are equivalent if they represent the same multiset of variables, meaning they contain the same variables with the same frequencies, even if their structures differ. To solve this, we use a function called collect_count to traverse each tree and count the frequency of variables in a dictionary. Once we have these counts for both trees, we simply compare the dictionaries to check if the trees are equivalent. For example, consider two trees. Tree 1 has a root node with the plus operation and children at nb, while tree 2 also has a root plus but with children b and a. Even though the order of the variables differs, they represent the same multiset, so they are equivalent. Let's break this down further step by step. The process begins by collecting the counts of variables for each tree. Starting with tree 1, we initialize an empty dictionary count and a stack containing the root node. We pop the root node, which is the plus operator, and push its children, a and b, onto the stack. Next, we pop b from the stack, a leaf node, and update the count dictionary to b1, then we pop another leaf node, and update the dictionary again to b1, 1. The stack is now empty, so we have completed the traversal for tree 1. We repeat the same process for tree 2. The root node is popped and its children, b and a, are pushed onto the stack. This time, we pop a first, updating the dictionary to 1, then b, updating it to 1, b1. With both trees traversed, we compare their dictionaries. Since both are 1, b1, the trees are equivalent, and the function returns true. In this example, the function ultimately returns true, as the two trees are equivalent. Now, consider another case where the trees are not equivalent. Tree 1 still has the root node plus with children at nb, but tree 2 has the root node plus with children at nc. As before, we start by collecting counts for tree 1. The process is similar. We initialize the dictionary count and stack, pop the root node, push its children onto the stack, then update the dictionary as we process the leaf nodes. The result for tree 1 is the dictionary, b1, 1. For tree 2, the process of collecting counts begins similarly. We initialize an empty dictionary and stack, pop the root node, and push its children, a and c, onto the stack. First, we pop c, a leaf node, and update the dictionary to c1, then we pop another leaf node, and update the dictionary to c1, 1. At this point, we compare the dictionaries from both trees. Tree 1's dictionary is b1, 1, while tree 2's dictionary is c1, 1. These are not equal, as tree 1 contains b while tree 2 contains c. Therefore, the trees are not equivalent, and the function returns false. Now let's examine a case with larger trees. Tree 1 has a root node plus with a left child that is another plus and a right child b. The left plus has two children, both a. Tree 2 also has a root plus with a left child and a right child that is another plus. This inner plus has children b and a. To collect counts for tree 1, we start with the root node and initialize the dictionary and stack. After popping the root, we push its children onto the stack. We process the right child b first, updating the dictionary to b1, then we process the inner plus, pushing its children and a. Each is processed in turn, updating the dictionary to b1, 2. At this point, the traversal for tree 1 is complete, and the final count is b1, 2. For tree 2, the process of collecting counts is similar but follows the structure of this tree. We start with the root plus and push its children onto the stack. The left child is processed first, updating the dictionary to 1. Next, we process the inner plus, pushing its children b and a. Popping a updates the dictionary to 2, and popping b updates it further to 2, b1. With the stack empty, the traversal is complete, and the final count for tree 2 is 2, b1. Comparing the counts from both trees, b1, 2 for tree 1 and 2, b1 for tree 2, we find they are equal. This means the trees are equivalent, and the function returns true. To analyze the time complexity of the check equivalence function, we start with the helper function collect_count. This function employs a stack-based iterative traversal to go through every node in the binary tree. For a tree containing n nodes, each node is pushed onto the stack once and popped once, resulting in n operations for stack management. Additionally, the operations performed inside the traversal loop, such as checking if a node is a leaf and updating the dictionary, are constant time operations, O1, for each node. Combining these, the time required to traverse the tree and construct the dictionary is O(n). Now, in the main function check equivalence, the helper function is called twice, once for each tree, with n1 and n2 nodes respectively. This results in a total time complexity of n1 plus n2, for building the dictionaries. Once the dictionaries are created, they are compared by checking all keys and values. If there are k unique leaf values, this comparison takes k time. In the worst-case scenario, with a constant-sized alphabet for leaf labels, k is bounded, and the comparison step simplifies to O1. Summing these steps, the overall time complexity of the check equivalence function is O, n1 plus n2, where n1 and n2 are the number of nodes in the two trees. Shifting focus to the space complexity, it is influenced by the stack used during traversal and the dictionary storing leaf counts. Starting with the stack, in the worst-case scenario of a completely unbalanced tree, the stack will hold all nodes along the longest path, requiring O, h, space, where h is the tree's height. For a balanced binary tree, the height is O, log n, but for a skewed tree, h can be as large as n, leading to O, n, space usage in the worst case. Now, the dictionary storing counts for unique leaf values uses O, k, space, where k is the number of unique leaves. In the worst case, if all nodes are unique leaves, k equals n, resulting in O, n, space for the dictionary. Combining these factors, the space complexity can be expressed as O, h plus k, which in the worst case becomes O, n. Finally, the overall space complexity simplifies to O, n plus k, where n is the total number of nodes and k is the number of unique leaf values. For scenarios with a small alphabet of leaf labels, k becomes constant, reducing the space complexity to O, n. Comparing this to a brute force approach, a naive method might involve generating all possible expressions from both trees and comparing them. This approach would be highly inefficient, with exponential time complexity due to the combinatorial explosion of possible expressions. In contrast, the optimized approach leverages count dictionaries to avoid generating expressions explicitly, reducing the problem to a linear tree traversal with a time complexity of O, n1 plus n2. Considering different cases, the best case occurs when both trees are empty, requiring only O1 time and space. In the average case, with balanced trees having n nodes, the time and space complexities are O, n. In the worst case, with skewed trees and all unique leaf nodes, the time complexity remains O, n1 plus n2, but the space complexity reaches O, n, due to the increased stack usage. When working with expression trees, there are several common mistakes to watch out for. First, it's important not to confuse structural equivalence with functional equivalence. Two trees can have different structures but still evaluate to the same result, like A plus B and B plus A, in the case of addition. Similarly, the commutative property of operators like addition and multiplication means that the order of operands doesn't always matter. Failing to account for this can lead to errors when comparing trees. Another issue arises with operator precedence. For example, A plus B asterisk C is not the same as A plus B asterisk C, because multiplication takes precedence over addition. Additionally, generating string representations of trees without standardizing the order for commutative operations can produce mismatches, even if the trees are equivalent. Finally, don't overlook edge cases like null trees or trees with only a single node. These scenarios require explicit handling to ensure correctness. Now, let's consider some interview-focused insights for tackling these types of problems. Many expression tree challenges test your ability to move beyond simple traversal and recognize deeper properties such as commutativity, associativity, and precedence. Breaking down complex trees into smaller, canonical forms, like sorting operands for commutative operations, can simplify the problem significantly. However, it's also important to evaluate trade-offs. For instance, brute force methods, like generating string representations for comparison, might be straightforward to implement but can fail to scale efficiently for larger trees. On the other hand, optimized approaches, such as hashing subtree expressions, are more efficient but come with added space complexity. Finally, always prepare for edge cases in your test scenarios, such as single-node trees, deeply nested structures, or trees with equivalent subtrees arranged differently. These are often used to test the robustness of your solution. There are also related problems that can help you strengthen your understanding of expression trees. For example, LeetCode 100, same tree, is a simpler problem that checks whether two binary trees are structurally identical. LeetCode 226, invert binary tree, can help you practice tree traversal and transformations. Similarly, LeetCode 114, flatten binary tree to linked list, focuses on tree structure manipulation, while LeetCode 297, serialize and deserialize binary tree, involves tree representation and equivalence. As for alternative approaches, the canonical form method involves reducing each subtree to a consistent form, such as sorting operands for commutative operators. This avoids reliance on string generation but can be more complex to implement. Another option is hashing subtrees, where unique hashes are computed for each subtree and compared instead of strings. This reduces time complexity but requires extra memory and careful handling of potential hash collisions. Finally, recursive comparison allows you to directly compare subtrees while accounting for commutativity and precedence. This approach is simpler and space efficient but may not perform as well for very large trees due to deep recursion. Great job! Today we learned how to check if two expression trees are equivalent using systematic traversal and comparison. Remember to keep practicing and exploring tree-based problems to strengthen your data structures knowledge. Thanks for watching, and see you in the next session. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!